My, my name is Ugwueze Kingsley. I am here to present a paper titled Modeling Cache Performance for Embedded System. The presentation layout is as follows: Introduction, Literature Review, Methodology, Cache Model Result and Discussion, Conclusion and Recommendations. Introduction. Computer cycles get faster at much more rapid rate than memory. In order for historical computer performance gain to continue, memory latency and bandwidth need to continue to improve. The most common way to provide this performance is to use small but very fast memory device to store the most commonly used data called caches. Cache performance relies upon locality. This locality is the predictable way in which cache tends to access memory element that he has accessed in the past or near those previous accesses. Of fundamental importance to improving a complex device is understanding how that device functions. This work contributes to that understanding in two ways. First, it expands upon an old and mostly unused model of locality called stack distance, and show how that locality interacts with various types of cache, including various types of cache configuration. Secondly, in this study, we present a cache performance modeling. We present a cache hit rate estimation model that will help computer architects in their design. From our review, we find out that there is need to understand cache memory behavior and to evaluate its performance, and also the need for optimal cache design to increase efficiency. The aim of this study is to present a cache performance model for embedded systems. The specific objective of the study are as follows: to develop an analytical cache hit rate estimation model, to characterize the locality of embedded system workloads, to develop a model using metrics from characterized embedded system workload and compare results using standard cache simulator. In this study, data cache of a single core embedded processor system were considered. Also, the cache configuration considered was set associative with least recently used replacement policy. Many concepts related to this study were reviewed, including the underlisted: concept of cache memory, memory wall problem, embedded system, cache performance, application locality matrix, and cache model. Related works. A number of literature related to this work were reviewed. Here we present a few that lead to the research gap which is addressed in this study. Martin et al. In storage hierarchy developed an algorithm to calculate stack distance of application memory reuse. This stack distance is the same with reuse distance as used in this study. They did not propose cache performance model. Brehop and Embody in their study also use stack distance matrix. They characterize application reuse distance. Their work targeted desktop-like computer. They developed a stack distance distribution model and proposed a model to calculate hit probability for any given stack distance. In another work, Beckman and Sanchez used locality matrix called reuse time. They proposed a cache performance model with the matrix. They characterize the application using hardware monitor, and their work target desktop-like computer. They also model cache behavior for other replacement policy. In the work of Pan and Johnson, they used reuse time matrix, and they propose a probabilistic cache performance model based on Markov chain. Just like this present study, they use interpin to characterize application. Their work targeted desktop-like computer. Methodology. The following steps were used in this study. First of all, a binomial statistical tool was used to model cache performance, and the application were characterized using pin tool called Mica. And after that, a cache hit rate estimation model were proposed. The cache hit rate estimation model were evaluated using embedded workload, and the result compared with sim-cheetah simulator. For the purpose of evaluating and comparing the model presented in this study. The MI benchmark suit were selected as choice benchmark. Selected benchmark for this study are as follows: byte count, basic math, FFT. The host configuration of the configuration of the host computer that were used in this study is shown in the table below. Method of metric collection and memory characterization. Microarchitectural independent characterization of application (MICA-PIN2) were used to characterize application. The memory reuse distance of application were characterized. The characterized reuse distance were grouped in 18 buckets or bins. The midpoints of the bins were used to represent the bin. These reuse distance were used to plot histograms. Evaluation of the model. The characterized reuse distance were used to evaluate the model. Cache parameter was also inputted into the model. Cache size considered are 4 kilobytes, 8 kilobytes, 16 kilobytes, 32 kilobytes, and 64 kilobytes. Cache configuration considered are 2 ways, 4 ways, 8 ways, and 16 ways for each size of cache. LRU's replacement policy were adopted. All cache line size is 32 bytes. Table and graph were used to show results. Comparison of model results using sim-cheetah. Sim-cheetah simulator was configured to align with the evaluation parameter, and the results obtained for every benchmark were used to compare the results from the cache hit rate estimation model. Results were shown in table alongside the evaluated results. Errors were calculated. Assumption for the model development. The study assumed that memory accesses are mapped into various cache lines randomly, and that mapping of cache line into various cache sets are assumed to be random. Also, the reuse distance distribution are assumed to be identically and independently distributed. Modeling cache hit rate. For a given reuse distance profile of an application, the distribution is given in equation 1 for every reuse distance d. The cumulative reuse distance is defined as the probability of obtaining at most the reuse distance d in entire memory accesses, as shown in equation 2. If the probability of cache accesses being in cache set X is P, assuming to be success probability, and the probability of access not being in cache set X is Q, assumed to be failure probability, it can be stated in form of binomial probability by finding the probability of obtaining a success after the reuse distance trial using Bourneli trials as shown below in equation 3. To be able to calculate the probability of hit in reduced distance that is greater than or equal to associativity A, we use the cumulative binomial probability given in equation 4. And the hit rate estimation for such reduced distance is given by equation 5 after substituting for P and Q. The hit rate estimation for all reduced distance that is equal to the degree of associativity and above is as shown in equation 6. Finally, the overall hit rate estimation model of an application derived by obtaining the cumulative reduced distance distribution up to A minus 1 and adding equation 6 is given by equation 7. Equation 7 gives the cache hit rate estimation model. Characterization of embedded benchmark. The reduced distance result of selected MI benchmark were characterized using MICA-PIN2. The characterized reduced distance results were grouped into class interval. The midpoints of each class interval were calculated and used to represent the class. These midpoints were used to plot a reduced distance histogram for the selected benchmark. Figure 4.1, 4.2, and 4.3 below show the characterized results and their histogram for respective benchmarks. The histogram for bitmark benchmark is at the right, while the characterized results are in the left. These are for basicmath benchmark. Figure 4.3 is for FFT benchmark. The characterized result and the histogram is as shown in this slide. Model evaluation and comparison of results. To evaluate the model, the characterized reduced distance midpoint were used. Cache configuration parameter and reduced distance were input into the model. Results were calculated for the choosing cache configuration for selected benchmarks. Sim-cheetah simulator was used to compare the result of the model. The simulator was used to run the benchmark for choosing cache configuration. To evaluate results for the model developed was shown in table. The evaluated result for the model developed were shown in table alongside the result from the simulator. Also, the error between the two results were calculated as shown in the same table with the result. The result for both hit rate estimation model and sim-cheetah simulator were plotted against various cache configurations. The model mean error for each and all the benchmarks were calculated. The result table and graph for the three benchmarks are shown in figure 4.4, 4.5, and 4.6. Figure 4.4 shows the result for bitcount benchmarks. The graph is at the right hand while the results are in the left hand of this current slide. Figure 4.4 is the result for basicmath benchmark. This is the result and the graph is as shown. Figure 4.6 is the result for FFT benchmark, and this is the results, the results and the graph. Summary of the results. Bitcount benchmark has the best locality, hence best performance. Basicmath benchmark has the worst locality. The results show that the mean error of the cache hit rate estimation model for basicmath, FFT, and bitcount benchmark are 2.441%, 1.900%, and 0.027% respectively, as compared to results from sim-cheetah simulator. The mean error for the three benchmark is equal to 1.456%. Conclusion and recommendation. Cache hit rate estimation model was proposed. The embedded workload were characterized using MicroPin to collect reduced distance matrix. The reduced distance with cache configuration parameter were applied to evaluate the cache model to estimate cache hit rates. It showed that smaller the reduced distance, the better. The model results were compared with results from sim-cheetah. The margin of error were below 5%, which is acceptable. Contributions to knowledge. The proposed cache hit rate estimation model for embedded system will help computer architects in their designs. Recommendation. Modeling of a reduced distance based cache model for multi-level cache is recommended. We also recommend for modeling of cache performance behavior of a multi-core embedded system based on reduced distance. Finally, we also recommend for modeling of cache performance of a single core embedded system based on reduced distance for other replacement policies. This is the references in this current slide.